Well, here we are at Voltaic Cells. I tell my classes at the beginning of the year that eventually I'm going to show them how batteries work, and I look forward to that all year long, and here we are. 12.03 Voltaic Cells, portable power for the masses. Now, understand that the battery technology I'm going to show you here is ancient technology. We don't use batteries of the design you're going to see the way we do now. For example, the battery that's in your phone is not what I'm going to show you in this diagram, but it works on exactly the same principles. It's just engineered differently so that it can fit inside of your phone. So we can use oxidation and reduction reactions to generate electricity. For example, if I take zinc and put it into copper nitrate, I'm going to get an exchange of electrons. If we put the zinc directly into the copper sulfate, the zinc will be oxidized, positive 0.76 volts. The copper will be reduced, positive 0.34 volts, and we'll get a positive 1.10 volt cell. Okay, that's actually what you call it. Like, for example, double A's and triple A's, they aren't batteries, they're cells. A battery would be if you hook up a bunch of cells together to get higher voltage. For example, a 9-volt battery is made up of 6 small 1.5-volt cells all connected together. So what we're going to be dealing with here are called cells. We call them batteries colloquially, but it only really applies in the case of a 9-volt battery or, let's say, a D-volt battery. A 6-volt battery. Also, in your cell phone, those would be batteries also because they're made of multiple individual cells. Now, if we were to place the copper directly into, the zinc directly into the copper nitrate, what would happen is not this. Okay, if we put zinc directly into copper nitrate, we will get an exchange of electrons. The problem is the exchange of electrons happens directly between the metal strip and the copper ion. You can see the electron being transferred directly from zinc to copper. That's not going to help us if we want to make electricity. We need a way of separating the zinc from the copper so that we can make the we can actually capture the electrons as they go from the zinc to the copper. So what we need to do is design an electron trap. Here's what we can do. Put the zinc and the copper ions in different containers instead of trying to react them together. So let's take this zinc strip and take it out of the copper nitrate and put it instead into a beaker containing zinc nitrate. Now, why would we do that? Zinc won't react with zinc nitrate. You'd get a voltage of 0. That's exactly the point. We want zinc to go into a solution that conducts electricity. The problem is zinc will oxidize in most solutions, so we want to guarantee zinc will not react with the solution. So we put it in a solution containing its own ion. Then into the copper nitrate solution, we put a strip of copper. Now, this copper is not part of the reaction. The copper strip is there to capture the electrons coming from the zinc. The reason we don't use any other metal is because any other metal will react with the copper nitrate. We don't want this metal electrode to react with the solution, so we make it the same metal that's in the solution. So zinc will go into zinc nitrate, copper will go into copper nitrate. You'll connect the two metal strips with wires, and then if you want to calculate the voltage, you don't have to. You can directly measure it by putting a voltmeter. We call any device that's powered by a cell a load. So, for example, your cell phone is a load that's powered by the battery that's in your cell phone. So, any device that's powered by a battery is considered to be a load. However, this will not be enough to get the voltage to drop. Our metal strips may be connected, but we have a broken circuit. The circuit must be complete. So how do we connect the two solutions? We've connected the two metal strips. How do we connect the solutions? Well, we use what's called a salt bridge. Now, a salt bridge can take many forms, from an electrolyte gel to a semi-permeable polymer barrier. But for the purposes of this wet cell, we're just going to use a tube that's filled with, well, some sort of ionic compound dissolved in water. What I usually do is I take a paper towel and roll it up and soak it in salt water and just put it between the two beakers. And you can see now the voltmeter is actually popping out voltage. But why should this work at all? What's actually happening? Well, I want to show you exactly what's taking place here. The zinc gets oxidized. We know that already. The electrode where oxidation takes place is called the anode. And in a battery, we designate that as the negative terminal of the battery. That doesn't mean it has a negative charge. We had to call it something. You know how when you plug a battery in, you see where it says negative and positive, so you know what direction to plug the battery in? Well, that's all this is. We label it negative so that we know where to plug it in. Now, what happens is the zinc undergoes oxidation. The zinc loses electrons. The zinc dissolves, so over time the anode will get eaten away, and the electrons that are lost by the zinc will travel through the wire, being pulled by the copper ions in solution. Now, the copper metal strip can't gain those electrons. Metals can only lose electrons. They can't gain them, but metal ions can. So the metal ions, the copper ions in the solution, pick up those electrons and are reduced into copper, which coat onto this copper strip, making the copper strip get larger. So the copper ions come over to the copper strip, gain the electrons, and turn into solid copper. Then the nitrate ions go through the salt bridge to complete the circuit. And that is the completed reaction. And this just continues to happen constantly until eventually either the anode gets completely dissolved or all the copper ions in the cathode get reduced. The anode is the negative electrode, the cathode is the positive electrode, and electrons always flow from anode to cathode through the wire and through the load. You start at the anode, electrons are lost there and go through the wire and through the load on fire. They enter the cathode, reduce the cations, and the anions go through the salt bridge back to where? Where we start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode, reduce the cations, and the anions go through the salt bridge back to where? I have a music video on this called You Start at the Anode. So I would check my YouTube channel for that video and then learn it because it can really help you. So I'm going to show you in detail using these particle diagrams exactly what's happening through each step of the way. So in this particular electrochemical cell, which is a generic term for any cell that has electricity associated with it, these are the parts that we have. All right, I've shown you all of these various parts. So the zinc anode is going to lose electrons and turn into zinc ions. The electrons will go through the wire and through the measuring device, the load that we'd plug in here. Here's a load measuring in volt. Or perhaps you can even measure the amps if you want to measure the current. Now, what happens is the electrons enter the copper cathode, half cell. The copper ions from the solution come to the electrode, and as soon as they touch the electrode, the copper ions gain the electrons, and then the negative ions travel through the salt bridge, which has the purpose of not only transporting electrons, but maintaining electrical neutrality. You see, not only do negative ions go through the salt bridge, positive ions go the opposite way through the salt bridge. So I'm going to take you on a journey one part at a time to show you what's going on. We'll start at the anode. Electrons are lost there. So let's zoom in and see what's going on. Here we have zinc ions and nitrate ions. We have zinc nitrate. We have the zinc anode. Zinc nitrate is ZnNO3 That's why there's two nitrate ions floating around. Now, what's going to happen is, as the zinc loses two electrons to the external cell, the zinc strip dissolves into the solution. So over time, the zinc strip will lose mass, because as the zinc loses electrons, the zinc ions dissolve into solution. Now, that's going to charge this solution positive, but don't worry, we'll take care of that later. Then, once the zinc has given up its electrons, the electrons travel from the anode to the cathode through the external circuit, through your load, which in this case is measuring 1.10 volts as the voltage. So you start at the anode, electrons are lost there and go through the wire and through the load on fire. They enter the cathode. So let's have a look at what's going on at the cathode. So in the cathode compartment, the copper strip itself doesn't gain the electrons. What happens is the copper ions are the blue ones in solution. As the electrons travel through the metal strip, the negative electrons attract the positive copper ions. The positive copper ions gain the electrons and form solid copper, which coats onto the metal strip. So over time, the size of the copper strip will increase, and the concentration of copper ions in solution will decrease. And you'll notice what's happening to the color of the solution. As copper ions leave the solution is getting more pale in color because the transition metal copper is exiting the solution. You can see just how much bigger this strip has gotten in this small period of time. So, what on earth does the salt bridge do? Well, again, it completes the circuit and maintains electrical neutrality. How does it do this? Well, we're going to take a look at each side of the salt bridge in turn. So if we zoom in, all right, the salt bridge maintaining electrical neutrality, if we zoom into the anode side, remember, on the anode, positive zinc ions come into solution. So negative ions from the salt bridge come out to cancel out the excess charge. So for every zinc ion that comes in, positive 2, negative 2 worth of charge has to come through. On the other side, as copper plus 2 ions leave the solution, a charge of plus 2 has to enter the solution from the salt bridge to maintain electrical neutrality. So for every positive ion that leaves, positive ions come in through the salt bridge to take their place. In this way, electrical neutrality is maintained. The anions will move towards the anode, and the cations will move towards the cathode. And finally, without the salt bridge in place, there can be no reaction. Remove the salt bridge, and your battery stops working because you've broken the electrical circuit. So how would you design your own cell? This is just a schematic of a voltaic cell. It doesn't matter where you label things. You can put your negative anode on the left, or you could put your negative anode on the right. Batteries are three-dimensional objects. You can look at them from the front, or you can look at them from the back. So left and right have no meaning when it comes to labeling your voltaic cell. The more active metal will be the negative anode, and it will be in a solution of that metal's ion. So let's just choose a more active metal. Let's say magnesium. We'll put the anode on the left side. We'll have magnesium immersed, it's the negative anode, immersed in a solution of magnesium nitrate. Why do I keep choosing nitrate? If you go to reference table F, you'll notice that nitrate is a negative ion that is always soluble. You could choose carbonate, but you have to first choose that the metal ion with carbonate is soluble, and it usually isn't. So I always use nitrate because it's a safe bet. Now, I could put magnesium as the anode and any metal underneath it as the cathode. We're going to choose, let's see, what are we going to choose? Silver as the cathode. Let's go for some bling here. So silver will be the positive cathode, and we'll immerse it in a solution of silver nitrate. Now, we start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode, reduce the cations, and the anions go through the salt bridge back to where? So the anions will go towards the cathode half cell to the anode half cell. The anions go towards the anode through the salt bridge, and the cations go towards the cathode through the salt bridge. Now, you could replace this with any two metals from this table. Let's say we had, say, manganese and tin. Manganese is the more active metal, so we'll have manganese and manganese nitrate, and we'll have tin here with tin nitrate. Let's say we chose potassium and sodium. Potassium's the more active metal. We'll have potassium and potassium nitrate and sodium nitrate. Of course, this is not practical because both potassium and sodium are group 1 metals, which violently react with water. So this design does have its limitations. That's all there is for voltaic cells. In the final topic, I'm going to show you how to decompose substances using electricity and how to use electricity to coat one metal onto another metal. We're almost done here, guys. Until next time, as always, fare thee well and bye.